Hi, my name is Oktay. Welcome to today's video about the lithium-ion battery and the newest research. This is a nice picture of a Chinese electric bus, the company Photon. It uses a LFP battery. LFP is a lithium iron phosphate. It has 303 kilowatt hours. It's from the company CATL, which is a big Chinese battery manufacturer. There's another Chinese bus manufacturer, that's Yuewang. To give you an idea about the size of this company has sold 479 electric buses just in Europe last year, 2022. This is the structure of the LFP battery, lithium iron phosphate. It's the same structure as olivine, which is magnesium iron silicate. There was a launch of the company CATL of a new LFP battery with a density of 500 watt-hours per kilogram energy density. This is a big deal because this means that now electric airplanes are possible. Recently there was a presentation of the chief scientist Wu Kai of the new Sijing batteries. They can quick charge 80% in just 10 minutes. This is a nice overview of the energy density in megajoule per liter versus megajoule per kilograms. Lithium-ion battery is here. The zinc-air battery is not too far away. At the right, that's hydrogen. Lithium has several advantages. One big advantage is its a low molar mass of just 6.9 grams per mole. That's less than 1/3 of sodium. It is a very tiny atom with just 3 electrons. The electron configuration is 1s2, 2s1. Lithium-ion battery is known for its high energy density. Other technologies are the zinc-air battery and the sodium-ion battery. This is a comparison of these 3 technologies. At the left, that's the sodium-ion battery. It has a cost advantage, especially recently because lithium prices went up. The sodium-ion battery does not contain lithium. In the middle, that's the NMC battery. That's nickel, manganese, cobalt side. It has the advantage of the highest energy density. However, the elements, as you can see, nickel and cobalt are very expensive. At the left, that's the LFP battery, lithium iron phosphate battery. Here you can see one part is the iron phosphate. That's the lithium. And this LFP battery is cheaper than the NMC battery, and it is safer. And you can see a very interesting thing, that's manganese. Here is a very low percentage of the costs. So in the future, the LFP battery could be improved to the LMFP battery, which is a lithium manganese iron phosphate battery. And this would give you a bit higher energy density. This is the abundance of the elements lithium, sodium, and zinc in Earth's crust. You can see lithium is here. This y-axis is a logarithmic axis. Sodium is here. You can see that's about 1,000 times more abundant than lithium. This is a big advantage. And the reason is lithium can be destroyed by some nuclear reactions. For example, if it's hit by a proton, then you get beryllium, and this beryllium decays to helium isotopes. And zinc is here, about the same as lithium, bit less than lithium. But lithium is not so rare, so enough lithium for batteries available. And the current trend is hybrid battery. For example, you could use 1/3 lithium batteries, lithium-ion battery, plus 2/3 sodium-ion battery. This is another type of battery, that's a solid-state battery. is a potential successor of the lithium-ion battery. There is a work of Yuewang, Sijing Liu, and Baoling Huang from Hong Kong, China. They made a quasi-solid-state gel-polymer electrolyte. This gives the battery high cycle stability and safety if you use fluorine polymers, for example PVDF, which is polyvinyl vinylidene fluoride, CH2CF2N. This gives this type of battery a high thermal stability below 200 degrees Celsius. And this is a worst case scenario for batteries. That's the formation of dendrites. If they pierce through the separator, then you get a short circuit and fire. However, with the gel electrolyte battery, this is not possible. This is a picture of the sodium-ion battery. There's another work of Rastislav, Turányi, and Sanghamitra, Mukhopadhyay from UK. You can see the components of the sodium-ion battery: additive, binder, solvent, salt, anode material, carbon, metal oxides or metal alloys, cathode material, oxide with layer structure, or polyanions. And these scientists made a neutron spectroscopy of the battery materials, and the techniques X-ray and neutron spectroscopy nicely complement each other. This is an example of the sodium cobaltate layers of oxide, here in red, cobalt in green, and sodium in blue. And there are different types of stackings with different properties. The lattice types depend on the sodium concentration. These are three examples. There's called O3, which is layer type ABC, P2, ABBA. This is if X is between 0.6 and 0.7. And another type is E3 with the layers ABB, CCA. This is a phenomenon called hysteresis. For example, elastomer has this phenomenon. This is a dependence of the state of a system on its history. This phenomenon can be seen in physics, chemistry, biology, and other areas. There's another work of Lukas, Köbbing, and colleagues from Germany. They made a research on the element silicon, which is a very good anode candidate. However, there are problems with high expansion and constriction, and this material has a voltage hysteresis. But there's a trick, and the trick is using silicon nanoparticles that are not bigger than 150 nanometers. These are stable. And these scientists propose using a viscoelastoplastic silicon to solve this problem with a solid electrolyte interface to avoid the stress during charging and discharging. There's another type of battery, that's the NMC battery, lithium, nickel, manganese, cobalt oxide. This type of battery has, for example, a graphite anode. There's a work of Heng Chen and colleagues from Singapore. They made a first principles calculation of lithium niobate and tantalate coatings. And they found out that a multiphasic niobate coating of lithium NbO3 gives a stability, and lithium NbO4 improves the conductivity. That's the best combination according to this scientist. This is another type of battery, that's the organic radical battery, ORB. It was developed in 2005. It has a high potential. There's a work of a group with Martin Ademer from Germany and Taiwan. They use a PTMA polymer backbone. PTMA is poly-tetramethylpiperidine pyridinyl oxyl or yl methacrylate. And according to this word, cross-linking this PTMA gives you a pore network, and a better 3D electrode microstructure makes the battery more efficient. This is an example of zero-strain materials, ZS. One such example is lithium titanium oxide. This is an interesting anode material. There's the work of A.F. Baumann and colleagues from Germany. This is a picture of layers of aluminum chloride as an example. These scientists made first principles analysis of electron structure and volume change during lithium intercalation. Intercalation means if the atoms get into the layers. And they found out that lithium, calcium, manganese fluoride, hexafluoride, is a promising zero-stain cathode material for the lithium-ion battery. This is a nice picture of the zinc-air battery. The work of Niklas J. Hermann and colleagues from Germany. They investigated the cycling mechanism of manganese dioxide cathodes, and they used the DFT, density functional theory calculation, and they found out that the insertion of protons is favorable over the insertion of zinc ions. This is a nice example of the use of the LFP battery. That's the BYD electric bus, BYD Build Your Dreams, in Costa Rica. And this is a very good combination because Costa Rica is already at 100% renewable energies. This is a big advantage, not only environmentally, but also economically. I would like to dedicate this video to Professor John B. Goodenough. He lived from 1922 to 2023. Professor Goodenough was the winner of the Nobel Prize in Chemistry in 2019. And he got this prize for his fundamental research on the lithium-ion battery. There's an interview about the fundamental science of Professor Goodenough. I will put the link into the description together with his scientific papers. You can check it out if you're interested. That was today's video about the lithium-ion battery and the newest research in this field. Thank you for watching. Have a nice day. Bye-bye.